Scientific notation, know it, use it. Loving it is purely optional. It's me, Moser. After this video, you should be able to correctly use scientific notation to represent both very large and very small numbers. You should also be able to use scientific notation to perform mathematical operations. You should already know how exponents work, and it'd be dandy if you knew how to add, subtract, multiply, and divide small whole numbers. Yeah, that would be good. So in science, we very often end up handling numbers that are very, very large, like this one, or very, very small, like this one. And these numbers are awkward. I mean, how do you even say the name of that number? You can say 526, you can say 7,302, but how do you even say this? How do you even say this one? How do you multiply and divide those things easily? There aren't enough spaces in the calculator. Good thing we've got a tool. Scientific notation. Scientific notation is a simple method that relies on exponents and base 10 to make writing and handling very large and very small numbers very easy. So let's take 327. Now, obviously this one isn't so terrible. We could deal with this as is, but if we're going to put this into scientific notation, and it is a good first example, we could factor out a 10, couldn't we? Or a couple of 10s? Well, isn't 327 actually the same thing as 3.27 times 10 times 100? It is. And isn't 100 the same thing as 10 times 10? It is. So 327 is the same as 3.27 times 10 to the times 100, which is the same as 3.27 times 10 times 10, which is the same as 3.27 times 10 squared, 10 to the second. That's scientific notation. It's not hard. Before we go any further, I want to look at the pieces of any number that's in scientific notation. So this part here in front that you're multiplying by 10 to the something is called the coefficient. 10 is the base. We're multiplying by something in base 10. And the power that 10 is raised to is the exponent. Very often the base and exponent in scientific notation are called the power of 10 as a means of shorthand. There are some rules when writing numbers in scientific notation. And the first one, a very important one, is that that coefficient must have a single digit between 1 and 9 in front of the decimal. So 1.5 times 10 to the second is totally legal. 15 times 10 to the first? No, not at all. 9.999 times 10 to the fourth? Awesome! 999.9 times 10 to the first? No. 7.26 times 10 to the negative 11th? Sure, that's great. 0.726 times 10 to the negative 12th? Absolutely not. Always make sure that your coefficient has a single digit between 1 and 9 in front of the decimal. Now, I say in front of the decimal. There doesn't have to be a decimal. We can use a number like 5 times 10 to the fourth. That's fine, and you'll understand more about when we use numbers like that when we start talking about rules for significant figures. The second rule, though I guess it's not so much a rule as a thing to point out, the exponents on your base can be negative or positive. 10 to the second equals 10 times 10, or 100, so we're taking 5.2 and making it a larger number by multiplying by 100. But when we have a negative exponent, we're multiplying, for instance, 10 to the negative second is equal to 1 over 10 times 1 over 10, or 1 over 100. So we're going to be dividing that number by 100 and making it smaller. All right. The second rule, though I guess it's not so much a rule as a thing to point out, the exponents on your base can be negative or positive. 10 to the second equals 10 times 10, or 100, so we're taking 5.2 and making it a larger number by multiplying by 100. But when we have a negative exponent, we're multiplying, for instance, 10 to the negative second is equal to 1 over 10 times 1 over 10, or 1 over 100. So we're going to be dividing that number by 100 and making it smaller. All right. Let's start with the part that most people find the easiest, expressing numbers in scientific notation, basically taking numbers in and out of scientific notation. Well, let's say we're given this beauty right here, 75,260. The only real way to move the decimal, well, it looks so juvenile, but remember that your decimal's starting there. 1, 2, 3, 4. Yes, I just drew 4 little humps under the number. Well, that's what you got. What if I've got a number like this, 0.00375? Well, again, I'm literally going to draw bumps under the number. I'm moving the decimal 1, 2, 3. What does that give me? 3.75 times 10 to the negative third. Remember that your exponent will be positive if you're taking a large number and making it smaller. It will be a negative exponent if you're taking a small number and making it manageable. That part's pretty easy for most people. Now let's move on to doing operations with scientific notation. There are different rules for addition and subtraction, or multiplication and division, when we're working in scientific notation. So when we're doing addition and subtraction problems, your exponents have to match. When you're multiplying, exponents are simply added, and when numbers are being divided, the exponents are subtracted. Most people find the rules for doing operations with scientific notation for multiplication and division fairly easy. Very few people have a problem with that. Weirdly, doing addition and subtraction with scientific notation seems to throw a few more people for a loop, but that's okay. We'll give you a chance to practice. So let's look at an addition and subtraction problem. If we're adding 2.5 times 10 to the second and 5.0 times 10 to the first, what we have to remember is that we're actually talking about 250 and 50. Now, of course, in this example, you could easily fluff those numbers out, take them out of scientific notation, and just add them, but with much larger or much smaller numbers, that's often not an option. We have to make the exponents match, which means moving the decimal in the scientific notation so that we have this, 2.5 times 10 to the second plus 0.5 times 10 to the second. Wait a minute, Moser. I thought you said that everything had to have a coefficient with a single digit between 1 and 9 in front of the decimal. Well, yeah, when you're writing your final answer. But in these intermediate stages of addition and subtraction problems, you'll generally have one number that is not in correct form. It's okay. That allows us to then take the coefficients, 2.5 and 0.5, and add those and multiply the entire thing by our 10 to the second. And what does that get us? 3 times 10 to the second, otherwise known as 300. Cool. What if we have an addition problem like this? 7.21 times 10 to the fourth plus 8.3 negative fourth, plus 8.3 times 10 to the negative third. Well, it's helpful to remember, and of course in this example I can take these numbers out of scientific notation, that we're looking at numbers whose places are not aligned. That's really what that difference in exponents means. If I go ahead and add these up, which again I can do with this example, I've got an answer set aside. We'll see if I can match it when I use scientific notation to do this problem. Well, I know that this would give me 9.021 times 10 to the negative third. How about if I do it for real using the scientific notation? I can make these both times 10 to the third. I've got 0.721 times 10 to the negative third, 8.3 times 10 to the negative third, which gives me 0.721 plus 8.3, the whole thing, times 10 to the negative third, which gets me Look at that. How cool. Had you noticed that the two addition problems that I've done have featured numbers that were only 1 power of 10 off of one another? Meaning that their place values were only off by 1. What if I have something like this? 2.5 times 10 to the 5th plus 2.5 times 10 to the negative 4th. Well, remember, what we would really be adding if we added these numbers are 250,000 and 0.00025, which gets us, oh boy, a crazy number. If we rounded that number, and you don't know about the rules for rounding yet, but if we rounded that down to the 2 digits we had in our beginning numbers, we'd have 2.5 times 10 to the 5th. Wait a minute, that's what we started with. In other words, this is a crazy problem. You won't see these because adding this to a number that large is kind of like putting a drop of water on an elephant's back and seeing if it can tell the difference. You're not going to see stuff like that. Now, let's get on to the multiplication and division. Let's start with 1.3 times 10 to the 2nd times 2.8 times 10 to the 6th. Well, we don't have to do anything with those powers of 10. We can just multiply the coefficients, then add the exponents on the powers of 10, and we get a raw answer of 3.64 times 10 to the 8th. Again, you don't know the rules for rounding yet, but we'll just assume that we can keep the same number of digits we started with. So our final answer would be 3.6 times 10 to the 8th. These are easy. Everybody loves these. Let's do one that looks really simple on the face of it. 2.5 times 10 to the 1st times 5 times 10 to the 2nd. Remember that we're really multiplying 25 by 500 here. So we're going to get 12,500, but assuming we didn't know that, we would take our coefficients, multiply them, multiply the whole thing by our power of 10, adding our exponents because we're multiplying, and we get a raw answer of 12.5 times 10 to the 3rd. We're done, right? Well, the problem is that's not in correct form, so we're going to have to move the decimal. Now, my little feeble pea brain struggles with this, so I literally do this. I look at where the decimal is, and I imagine going 1, 2, 3, oh yeah, 1, 2, 3, 4. So the answer for this problem will be 1.25 times 10 to the 4th. Now, again, going with the rule of keeping as many digits as we started with, this becomes 1.3 times 10 to the 4th. What if we want to divide numbers that are in scientific notation? How about 6.2 times 10 to the 8th divided by 1.9 times 10 to the 6th? Well, again, divide the coefficients, multiply the whole mass by the base 10 with its exponents. Since we're dividing, we're going to subtract our exponents. Voila! 3.263, it goes on and on and on and on, times 10 to the 2nd. Of course, we're going to keep 2 digits, rounding, so we get 3.3 times 10 to the 2nd. Ah, that's so easy. What about 3.2 times 10 to the 4th? Divided by 4.3 times 10 to the negative 2nd. Well, again, divide your coefficients, multiply the whole mess by your power of 10 and exponents. Exponents here are subtracted because it's a division problem. And note that I tend to write out the minus a negative 2. I do that for a couple of reasons. Number one, it gives me a visual clue of where I got those numbers. If I go ahead and change that to a plus 2, I lose that visual clue. And if I get confused later, not a problem like this, but a more complicated one, that gives me a way to trace back to where the numbers came from. Okay, so anyway, do my division. I get 0.74418 times 10 to the 6th. Ah, crud, I gotta move a decimal. Well, again, I'll do my little humps and bumps under and over the number. What I end up with, whoops, 1, 2, 3, 4. So going that direction, 5, 6, I'm going to have to come back not quite as far. So this will be 7.44 times 10 to the 5th. My final answer, keeping only one place value, would be 7.4 times 10 to the 5th. Okay. What are the common mistakes that students make? Well, the first one is getting an answer with a coefficient under 1 or over 9 and forgetting to move the decimal. This doesn't mean you can't do the math, but it does mean you're not putting things in the correct form for scientific notation. And that form is actually important. Mixing up the rules for addition and subtraction with those for multiplication and division. Now this will get you a completely wrong answer. And the last common mistake that I tend to see is people ignoring the negative signs on exponents when adding or subtracting them. That's why I write my negative very prominently. All right. Do you feel like you can correctly use scientific notation to represent both very large and very small numbers? Can you use scientific notation to perform mathematical operations and avoid the common mistakes? Awesome. Get practicing.